Okay, now that we've had a look at these first four sections in Chapter 5, we're going to look at some examples. Mixed factoring. This goes along with your summary exercises here in the middle of Chapter 5. You have a handout that lists the 18 problems I'm about to work for you. If you don't have that handy and you want it, go ahead and pause and get that handout. We're going to take these factoring problems and work on identifying what type of factoring problem we're looking at. So number one. Now, first things first. Always, always, always look for a greatest common factor first. I don't care what the problem is, that is the first step of any factoring problem. Now, among these three terms, there is no greatest common factor other than one, and so there's nothing to factor out. So what type of problem do I have? This is a trinomial, and the leading coefficient is 1. So this is a problem that would come from section 5.2. When we have a trinomial whose leading coefficient is 1, we say, if this factors, it will factor as a pair of binomials, each starting with x. We can look and see, this tells me that my signs will be the same. This tells me, in fact, they will both be plus. And now I'm looking for two numbers. I'm looking for two numbers whose product is 60 and whose sum is 16. Hopefully those numbers pop right in your brain. Can you think of two numbers that multiply to 60 and add up to 16? How about 6 and 10? And we're done. Of course, if they don't pop right in your brain, you can always go down the list. Is it 1 and 60? Is it 2 and 30? Is it 3 and 20? Does 4 go into 60? Yes. 15 times. Is it 5 and 12? Is it, there it is, 6 and 10? And of course, if you run out of factor pairs, then you know that what you have is prime. Let's look at number 2. First things first, always check for a greatest common factor. I think this greatest common factor is fairly obvious. The greatest common factor between these two terms is 10. So factor out that 10. Now we say, will this factor any further? If it won't, put a box around it and that's your answer. But will this binomial factor any further? It's a binomial, so a couple questions come to mind. Is this a difference of squares? Actually, it is. The other things I might ask, is this a sum or difference of cubes? And of course, if it's a sum of squares, then we know it's prime and it can't go any further. We'd put a box around what we have, since I've already factored out a greatest common factor. So, here in the parentheses, a difference of squares, section 5.4. Our greatest common factor comes down, and a difference of squares, this is the square of z, 225 is the square of 15. So a difference of squares factors as the first plus the last, times the first minus the last. Nothing here will factor any further. And that one's done. Let's look at number 3. Feel free at any point to pause the video and give it a go yourself. And then come back and compare answers. I'm just going to keep working problems. Number 3. Check for a greatest common factor first. Well, 3 is prime. 3 is not a factor of 2 or 8. There's not an m appearing in every single term. The last term doesn't have an m. There's no greatest common factor here other than 1, so nothing to factor out. Now, what kind of factoring problem is this? I see 4 terms. I see 4 terms, and so we're going to try factor by grouping. Section 5.1. To factor by grouping, we group the first pair, and with respect to addition, we group the second pair. Of course, if that were a minus, we'd put plus a negative and keep the sign with its term. We take the greatest common factor out of the first pair. Out of the first pair, I can factor out a 3, and I see I've miscopied the problem. That should be an m cubed up front. I can factor out a 3 along with an m squared. Factoring that out, if I pull 3m squared out of 3m cubed, it leaves one factor of m, plus if I pull 3m squared out of 12m squared, pull 3 out of 12, it leaves 4, and I pulled both of the m's out, so no m's with that 4. In the second pair, I can factor out a greatest common factor of 2. And if I pull out a 2, it will leave m plus 4. I now have 2 big terms, and I see that their binomial factors match. So I will factor out that binomial factor. And what's it leave? 3m squared from the first term and plus 2 from the second term. Will anything here factor any further? Nope. So that one's done. Number 4. First things first, is there a greatest common factor? Well, let's see. Look at this 6. 6 is 2 times 3. 25 is not divisible by 2. 25 is not divisible by 3. So no, there is no greatest common factor other than 1 among these terms. This is a trinomial, and the leading coefficient is not 1, and so this is a problem from 5.3. We can attack it one of 2 ways. We can trial and error. She calls it FOIL. I call it unfoil. Most people call it trial and error. Or we can use the AC method. I tend to attempt trial and error first. And if I get stuck, then I'll switch over to my AC method because it is guaranteed. But trial and error is usually faster. If this factors, it will factor as a pair of binomials. Right here, this tells me my signs will be the same. In fact, my signs will both be minus. What else do we know? We have to start with a couple of W terms. And that's all I know. The rest of this I'm going to be guessing at. I need to figure out how this 24 is going to fall apart. I need to figure out how this 6 will fall apart, so that when I FOIL this back together, it will return that original trinomial. The 6 could be 1 and 6, or it could be 2 and 3. I don't know. Let's start with 2 and 3. Now this 24, we have several things to try. It could be 4 and 6, 6 and 4, 3 and 8, 8 and 3, 2 and 12, 12 and 2, 1 and 24, 24 and 1. In other words, the factor pairs are 1 and 24, 2 and 12, 3 and 8, 4 and 6. Those are the pairs that I need to try. However, I'll guarantee you right now, I don't even need to bother trying the 4 and the 6. Now, how do I know that? If I tried 4 and 6, well, look what I have here in my first factor. I have coefficients that are both even. There's a greatest common factor of 2, which did not originally exist in the original trinomial. Furthermore, I have a greatest common factor of 3 in this second binomial factor. Greatest common factors cannot just magically appear. If it was not already taken care of, it can't show up now. Even if I put the 6 first, I still have the issue. These are both even. Here's a greatest common factor of 2, which was not originally a factor of my trinomial. So that's not possible. I'm not even going to bother checking. And if I weren't doing this for the video, I wouldn't have even written it down. I would have said, it can't be the 4 and the 6. There's no way. And I would have moved on. What about the 3 and the 8? Well, here's another thing I know. It cannot be 8 and 3. Because look at this second factor. I would have all of a sudden a greatest common factor of 3, which did not originally exist. We can't go around creating magic greatest common factors. But maybe this will work if I put the 3 here and the 8 there. How do we know? Well, we check the outside and inside. We actually check these because it's trial and error. We know that the first is right for FOIL. We designed it that way. We know the last, that positive 6 is the negative 2 times the negative 3. That's the last of FOIL. And do the outside and the inside, when combined as like terms, give me back that minus 25W. The inside is minus 16W. The outside, minus 9W. A total of minus 25W. So this must be how it factors. Nothing there will factor any further, and so we're done. Notice, I could have kicked out the 2 and the 12 as well, completely, because I could not have put a 2 or a 12 with this 2. The 1 and the 24, I couldn't put the 24 with the 2. I couldn't put the 24 with the 3. They would create magic greatest common factors. So if the 6 is going to be 2 and 3, out of all these possibilities, really the only thing that could possibly work is a 3 up front and an 8 in the back. If this hadn't worked, what would we have done? We would have said, well, it's not 2 and 3, maybe it's 1 and 6, right? Because our factor pairs, we had tried the 2 and the 3, and if we exhausted those possibilities, we would then try a 1 and a 6. But we found what we needed, and it's factored. Number 5. Always check for a greatest common factor first. There is no greatest common factor among these 3 terms. So what kind of problem is it? This is a trinomial whose leading coefficient is 1. This is from section 5.2. If this factors, it will factor as a pair of binomials, each starting with S. Right here, my signs are the same. In fact, they are both plus. And I'm looking for 2 numbers. I'm looking for 2 numbers whose product is 40 and whose sum is 11. Can you think right off the top of your head of what 2 numbers will do that? And as you know, if we ever get stuck, we just make a list of factor pairs. We know the 2 numbers I'm looking for are both positive, so we start with 1 and the product itself. Is it 1 and 40? Did those add up to 11? No. 2 times 20 is 40, but does that add up to 11? No. Does 3 go into 40? No. Does 4 go into 40? Yes, 10 times, but that's not a sum of 11. Does 5 go into 40? Yes, 8 times. Does that add up to 11? No. Does 6 go into 40? Well, if 3 didn't, 6 can't. Does 7 go into 40? No. Does 8 go into 40? Yes, it does, but I've already discovered that here at the bottom of my factor pairs. Once I make this U-turn at the bottom and come up with one that I've already discovered, I've run out of factor pairs. In other words, there are no two numbers whose product is 40, whose sum is 11. This cannot be factored, and so this one is prime. Number 6. Got way ahead of myself there. Number 6. First things first. Is there a greatest common factor among these three terms? Well, I'm suspicious. I see a 17. It's prime. So the only thing it could be is 17. 17 obviously goes into this last term 10 times. Now does 17 go into 51? 17 times 3. Is that 51? Sure is. 17 is the greatest common factor here. If I factor out a 17, it will leave me n squared minus, what did we say? 3 times 17 is 51. So minus 3n and minus 10. Now the question is, will this factor any further? Well, in the parentheses, I have a trinomial whose leading coefficient of 1. Once again, we are in section 5.2. If this trinomial turns out to be prime, I don't write prime for an answer. I've already factored once by factoring out that GCF. I'd put a box around this. But let's see if we can find two binomials that will multiply to give me that trinomial. Don't forget your greatest common factor out front. And if this trinomial factors, it will factor as a pair of binomials, each starting with n. This time right here, what? My signs will be opposite. And the larger the two numbers I'm looking for will be the negative, the larger absolute value. I'm looking for two numbers. I'm looking for two numbers whose product is negative 10, whose sum is negative 3. Can you think of any two numbers that do that? Hopefully very quickly you come to the point where you say, oh, positive 2 and negative 5. Pop those in and you're done. If you get stuck, you go down the list. Is it 1 and 10? We know one of them has to be negative. We said what? The larger one has to be negative. Is it 1 and negative 10? No. Does 2 go into 10? Yes, 5 times. Is it 2 and negative 5? Yes, those add up to negative 3. Now, in my mind, because they're opposite in sign, I think in terms of subtraction. I've got my signs in place already, so I'm just thinking I need two numbers that multiply to give me 10, and when I subtract them, they give me a 3. Well, that's 5 and 2. And then I'll look more closely at my signs and figure out which one gets the negative. The larger of the two absolute values gets the negative, just like we would have discovered here in our list of factor pairs. The 2 goes with the positive. You can always check these by multiplying them back out. Let's look at number 7. First things first, always look for a greatest common factor. Among these three terms, is there a greatest common factor other than 1? Well, you could look at this 6 and say that's 2 times 3. 2 doesn't go into 47. 3 doesn't go into 47. So no, there is no greatest common factor other than 1. I could also look at this 8 and say, that's nothing but 2 times 2 times 2, and 47 is not even. So again, no greatest common factor other than 1. So what we have here is a trinomial whose leading coefficient is not 1, section 5.3. I'll start with trial and error. If I get stuck, I'll switch over to AC method. Well, let's see. If this factors, it will factor as a pair of binomials, each starting with some q term. Signs will be opposite. And in section 5.3, this didn't tell us too much ahead of time. What it means is that the larger of the outside and inside will be the positive. But our signs are opposite, so we know this. We haven't guessed at anything yet. So we need to figure out how this 6 falls apart, and figure out how that 8 falls apart. For the 6, how about 2 and 3? For the 8, how about 4 and 2? No, definitely not. 4 and 2. There'd be a magic greatest common factor. That's not going to work, even if I switched them. 2 and 4. I still create a magic greatest common factor that was not originally there. So it can't be 2 and 4. Well, how about 8 and 1? Well, we can't put the 8 with the 2. Again, another magic greatest common factor. Okay, well then, let's try 1 and 8. Check the outside and inside. The inside gives me plus 3q, the outside minus 16q, a total of negative 13q, nowhere close to what we're after. Well, there's no other way to try the 8, is there? An 8 is either a 1 and an 8 or a 2 and a 4. The 2 and the 4 didn't work either direction. The 1 and the 8, the only way it could work is the 1 here and the 8 there. That didn't work. Well, then maybe it's not the 8 that's the issue. Maybe it's the 6. Instead of 2 and 3, how about we try 6 and 1? I won't write the 1 because it'll be that coefficient on the q. In other words, 6 is either a 1 and a 6 or a 2 and a 3. I thought I'd start with the 2 and the 3. So far I haven't found anything that works. Let's go ahead and try what we have here on the board. We've already got a 1 and an 8 in place, so might as well see if that happens to work. Product of the inside is plus q. Product of the outside minus 48q. A total of, hey, a total of minus 47q, but we're looking for plus 47q. What does that mean? The only thing is wrong with this would be my signs. That should be the minus. This should be the plus. Now when I check my outside and inside, I get minus q and plus 48q, a total of 47q. So that's how it factors. Notice that with this 6 running around, this was really the only other possibility. It couldn't be the 8 here and the 1 there, magic greatest common factor. And it couldn't be the 2 or 4 either direction. Can't put a 2 with the 6. They're both even. Magic greatest common factor. Can't put the 4 with the 6. They're both even. A magic greatest common factor. So this was the only other possibility. And it worked. Number 8. First things first. Always, always, always check for a greatest common factor. Among these terms, I see a lot of things going on, right? They're definitely all even, so there is a common factor of 2. They're also all divisible by 3. If they're divisible by both 2 and 3, then they're all divisible by 6. Is 6 the biggest? If I pull a 6 out of the 12, it leaves behind a 2. Pull a 6 out of the 18, it leaves behind a 3. 2 and 3 don't have any factors remaining in common, so 6 must be the biggest. Now, as far as the letters go, do they all have a factor of D in common? Yes, they do. Do they all have a factor of G in common? Yes, they do, and at most, one factor of G. Do they all contain a factor of A? Nope. Do they all contain a factor of H? Nope. So here's my greatest common factor. If I pull this out of each of these terms, I'm just dividing each term by this greatest common factor. What's left behind? Pull a 6 out of 12, it leaves a 2. Pull out the only D, no D's. Pull out 1G from G squared, it leaves a single factor of G. Not sure? Multiply those two things back together. It should give you back that term. And now plus, pull a 6 out of 60, it leaves 10. Pull a D and a G out of the rest of this, the only thing left is that A. Not sure? Multiply them back together, right? Should return that original term. And finally, pull a 6 out of the 18, it leaves a 3. Pull a D and pull a G out. All that's left besides my 3 is that H. Not sure? Distribute it back in. If I distribute this back in to this entire trinomial, it should return the original problem. Now, will this factor further? No. There's nothing here that suggests any type of FOIL, any type of grouping, any type of special factorization. That's just it. So this turns out to be just a 5.1 early problem. This is nothing but greatest common factor. That's the only thing we could do. But it is factored because I've written the original in terms of a monomial, what, times a trinomial. I've factored it into two factors that cannot be factored any further. Number 9. Greatest common factor? Nothing other than 1, so nothing to factor out. I see 2 terms, so I've got to wonder, is this a difference of squares? Clearly not. Is it a sum of squares? If it's a sum of squares, I could just say prime and be done with it. Well, 64 is a square, but 64 is a tricky one. He's a square and a cube. And u to the 3rd power, that's not a square. So what is this? This is a sum of 2 cubes. The cube of u and the cube of 4. Remember, it's 8 squared gives me 64, but it's 4 cubed. 64 is the cube of 4. Now, how does a sum of cubes factor? Whether it's a sum or difference of cubes, it will factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that. The last sign is always plus. Or some of you may remember that this is SOAP. Same, opposite, always plus. What goes in my blanks? The first, the last. The first squared. The first times the last. And the last squared. The first is that u. The last is the 4. The first squared, u squared. First times the last. Remember, this isn't double first last. This is not a perfect square trinomial we're talking about. This is just a plain first last. U times 4 is 4u. And the last squared, 4 squared is 16. I'll remind you again, Please don't write 4 squared. I'll take off points because you're not done. 4 squared is 16. I've told you already that the trinomial, the results from a sum or difference of cubes, will not factor further. And so that's it. We factored that sum of cubes. Number 10. Sorry, let me be consistent here. So this was a sum of cubes. This was section 5.4. Number 10. Is this a difference of cubes? Don't jump the gun. First things first. Is there a greatest common factor? Greatest common factor between these two terms is n. I can factor out a single n, leaving n squared minus 9. Now, am I done, or will this binomial factor further? This binomial is a difference of squares. The square of n and the square of 3. So this is also 5.4. We've got our greatest common factor floating out front. He needs to stay with us. And a difference of squares will factor as the first plus the last, the first minus the last. And that's it. Nothing there can be factored any further. Number 11. Is there a greatest common factor between these two terms? At this point, with your handout, these powers should be memorized. You should recognize that 169 is 13 times 13. That's its prime factorization, 13 times 13. 13 won't go into 100. And so there's no greatest common factor other than 1, nothing to factor out. Well, then we have a binomial. The one question we ask is this a difference of squares? It is a difference, and the first term is the square of 10k. The last term is the square of 13. And so this is a difference of squares, once again, 5.4. And this one is just as simple as the first plus the last times the first minus the last. Nothing there can be factored any further, and that one's done. Number 12. Is there any greatest common factor to factor out? No. 2 is prime, 2 is not a factor of 9, and so nothing other than 1. There's no greatest common factor I need to factor out. So, I have a trinomial whose leading coefficient is not 1. This is 5.3, which we can use either trial and error or the AC method. Let's see what we get with our trial and error. If this factors, it will factor as a pair of binomials, each starting with some v term, but I can do one better than that. 2 is prime. The only way that can fall apart is 2v times v. Right here, my signs are the same. In fact, right here, they're both plus. I haven't guessed at anything yet. Then what are the factor pairs I'm going to try for this 12? I could have 1 and 12. I could have 2 and 6. I could have 3 and 4. Those are all the factor pairs of 12. Let's start with the 3 and the 4. 3 and 4. Is it 3 and 4? Check the outside and inside. Inside is 3v, the outside is 8v, a total of 11v. That's not it. It's not 3 and 4. Maybe it's 4 and 3. No, it's certainly not 4 and 3. What do I have if I put a 4 with that 2v? A magic greatest common factor. So there's no point in even checking that. How about 2 and 6? Well, again, if I put a 2 with the 2, there's a greatest common factor of 2 that didn't exist. If I put the 6 with the 2, there's a greatest common factor that didn't exist. There's no point in trying 6 and 2 either direction. And then 1 and 12. Well, we know it can't be 12 and 1, magic greatest common factor. So it has to be, the only thing left is 1 and 12. The inside is plus v, the outside is plus 24v, a total of 25v. Still not what we're after. Did we miss something? Now, if you are convinced that we have missed nothing, then you might be ready to say this is prime. But if you have any doubt, did I miss any factor pair? You can always go back to the AC method. And you can say, okay, let me try it this way. I'm looking for two numbers. I'm looking for two numbers whose product is A times C. That's why it's called the AC method, right? A times C. 2 times 12 is 24. And whose sum is 9. My numbers will have the same sign. They'll both be positive. Is it 1 and 24? Nope, those don't add up to 9. Does 2 go into 24? Yes, 12 times. Those don't add up to 9. 3 goes into 24 8 times. Those don't add up to 9. 4 goes into 24 6 times. Those don't add up to 9. 5 does not divide 24. Does 6 go into 24? Yes, but I've already discovered that. I've made the U-turn here at the bottom of my list of factor pairs. There are no two numbers whose product is 24, whose sum is 9. This must be prime. And to tell the truth, with that trial and error that we started with, I'm convinced we tried every possibility. If you are convinced that you tried every possibility, you can go ahead and write prime. But if there's any doubt in your mind, you always have this AC method to fall back on. Number 13. First things first, greatest common factor. You should recognize 125 is just 5 times 5 times 5. It's 5 cubed, right? It's made up of nothing but 5s, and 5 won't go into 512. So no greatest common factor other than 1, nothing to factor out. Well, I've got a binomial. What kind of binomial do I have? Is this a difference of squares? No. Is this a sum or difference of cubes? I think so. It is a difference. Is this first term a perfect cube? Yes, it is. It's the cube of 5h. Is this last term a cube? Yes, it is. It is the cube of 8. So this is one of our special factorings, section 5.4, difference of cubes. A sum or difference of cubes will factor as a binomial and a trinomial. The sign in the binomial matches the sign of the problem. The first sign in the trinomial is the opposite of that. The last sign is always plus. Again, some of you may be saying SOAP to remember same, opposite, always plus. We fill in the 5 blanks. Do you remember what goes in the 5 blanks this time? The first, 5h. The last, 8. Right here, the first squared. You square 5h, you get 25h squared. The first times the last. 5h times 8, 40h. And finally, the last squared. 8 squared, is 64. And that's factored. And like we've said, that trinomial from a sum or difference of cubes will not factor any further, so we know we're done. Number 14. In number 14, is there any greatest common factor to factor out? Well, 49 is just 7 times 7. 7 doesn't go into 81, I know that much. And so no, there's no greatest common factor to factor out. So this looks like a 5.3 problem, a trinomial whose leading coefficient is not 1. But wait, are they jumping out at you? Do you notice that this problem starts with a square? It starts with the square of 7c. And it ends with a square. It ends with the square of 9. So I wonder, is this term in the middle, regardless of sign, double the first times the last? Let's see. 9 times 7 is 63. 63 doubled is 126, and times that c, 126c. Yes, that middle term is double the first times the last. This is a perfect square trinomial. That middle type problem in section 5.4. Well, I know how this factors. This factors simply as the first, and in this case minus, the last quantity squared. Can you work this one using the methods of 5.3? Yes, you can. And you'd be sitting here going, okay, if it factors as a pair of binomials, each starting with c. Signs are the same, they're both minus. 49 might be 7 and 7. 81, it might be 1 and 81, might be 3 and 27, might be 9 and 9. You might get lucky and hit it the first time. Nothing wrong with that, but we've already talked about the reasons for practicing looking for these perfect square trinomials, and boy, it makes quick and easy work. It makes quick and easy work. Of course, down here I wouldn't put a box around this until I've checked my outside and inside to see that minus 63c plus a minus 63c for my inside and outside do return that original middle term. I wouldn't use 5.3 for this. Nothing wrong with it, but man, that is quick and easy work if I spot those squares and it turns out the middle is double the first times the last. Number 15. Is there any greatest common factor to factor out? No. There's no greatest common factor other than 1. So we have a trinomial whose leading coefficient is 1. This is section 5.2. So if this factors, it will factor as a pair of binomials, each starting with an r. Right here, my signs will be opposite. And in fact, the larger the two numbers I'm looking for will go with my minus sign. I'm looking for two numbers. I'm looking for two numbers whose product is negative 18 and whose sum is negative 4. Can you think of what two numbers will do that? And remember, when they're opposite in sign, I like to think subtraction instead of addition. So in my mind, I'm going, okay, what multiplies to give me 18? And at the same time, when you subtract, you get a 4. Now, if you can find those two numbers, we'll figure out the signs in a minute. If you get stuck, you go down the list. Is it 1 and 18? And what do we say? Opposite signs, the bigger one's negative. Is it 1 and negative 18? No, those don't add up to negative 4. Is it 2 and negative 9? Those don't add up to negative 4. 3 goes into 18 6 times. Those don't add up to negative 4. 4 does not divide 18. 5 won't go into 18. 6 goes into 18. However, we already knew that. We've run out of factor pairs, meaning there are no two numbers whose product is negative 18, whose sum is negative 4. So this trinomial is prime. Number 16. Is there a greatest common factor I need to factor out? As far as the coefficients go, the leading coefficient is 1, so 1 would be the biggest. Do they all have a P? No. Do they all have a Q? No. The biggest thing they have in common is a common factor of 1. There's no greatest common factor then to factor out. And I see 4 terms. When I see 4 terms, I think factor by grouping. Section 5(1). Group the first pair, and remember, this is with respect to addition. Addition is associative, subtraction is not. So I need to make this into addition here in the middle, make this plus a negative, so that sign, that negative, can remain with that 4Q. Out of the first pair, I can factor out P squared, leaving Q minus 5. Out of the second pair, greatest common factor is 4. But can you look ahead and see? If I factor out just a 4, my signs aren't going to work out for my binomial factors to match. I don't need to factor out a 4, I need to factor out what? A minus 4, which will leave positive Q and minus 5. And so my binomial factors do match. I now have 2 big terms that have a common binomial factor of Q minus 5. Factor out the Q minus 5 and it leaves P squared minus 4. And we always ask, am I done? Not this time, are we? Look at this. One of my factors is a difference of squares. We always ask at the bottom of the problem, can anything here be factored any further? And this time the answer is yes. This difference of squares, the square of P and the square of 2. We've got our factor of Q minus 5. He floats into the next step. And this difference of squares will factor as the first plus the last times the first minus the last. Again, we ask, are we done? Or will anything here factor any further? This time we're done. Always watch, always make sure, because you know that when the instruction says factor, like all the way down your handout, when the instructions say factor, that means factor completely. Okay, so this was not only a 5.1, but it also had a component from 5.4 in it as well. Nice. A factor by grouping that ended up having a factor that was a difference of squares. Number 17. At a glance, you should be done. This is a sum of squares. The square of b and the square of 12. What do we know about a sum of squares? There's no greatest common factor to factor out. This sum of squares is prime. That's the end of that one. A sum of squares is prime. A sum of squares is prime. A sum of squares is prime. And finally, number 18. Always look for a greatest common factor first. I see all these terms contain an x, so I know I'm going to be factoring out an x. I see they're all even, so I know I could factor out a 2, but is that the biggest? Or are all of these divisible by 4? A number is divisible by 4 if it ends in a 2-digit number that's divisible by 4. 88 is divisible by 4. And right here, the last 2 digits, 88 is divisible by 4, therefore 288 is divisible by 4. These are all divisible by 4. If I factor 4x out of each term, it will give me x squared, here in the middle, minus 22x, plus, to divide by 4, cut it in half again. Half of 288, 144. Half of 144, 72. And we've pulled the x out. So we factored out a greatest common factor of 4x. The question is, will this factor any further? If not, put a box around it. But here in the parentheses, I have a trinomial with a leading coefficient now of 1. We need to check and see if it will factor. If it won't, that's our answer. If it will, we've got to get it factored. If this factors, it will factor as a pair of binomials, each starting with x. The signs will be right here the same. In fact, they will both be right there minus. I'm looking for two numbers. I'm looking for two numbers whose product is 72 and whose sum is negative 22. Now I've already got my negatives in place, so I can just think of it as I need two numbers that multiply to 72 and they add up to 22. And if it doesn't come to mind, what do? We go down the list. Is it 1 and 72? That does, and of course these would both be negative. My signs are the same, they're both negative. Those don't add up to negative 22. Is it 2 and 36? Those don't add up to negative 22. Does 3 go into 72? Yes. 3 goes into 72 24 times. That does not add up to negative 22. Does 4 go into 72? Of course it does. 2 went in and left an even number. So there must be another 2 available, right? Double the 2 to get 4, take half 36, and that's 18. And hey, those add up. Those add up to negative 22. Negative 4, negative 18. Nothing here will factor any further. And so that one's done. I hope this has helped you kind of see the process of tackling these mixed factoring problems. Keep practicing there in your summary exercises. Keep practicing, keep practicing, keep practicing. You know the sermon, right? If you can't factor, you're pretty much stuck.